Aloha and welcome to week 7, lecture 1. Here we're going to talk more about atmospheric circulation than the ocean. But atmospheric circulation is super important for learning how the ocean moves and how it transfers heat around the globe. So the atmosphere moves because of uneven solar heating. We've talked about this a little bit before, how the equator receives direct light and the poles receive very refracted light. We'll look at a picture of that again in a minute. And I'm sure you all know warm air rises, cold air sinks. That creates a pressure difference, and it means that the atmosphere is essentially always moving or trying to move warmer air toward the poles. So here's the angle at which sunlight hits the equator straight on, a little less in the mid tropics, and significantly less around the poles. So we're getting more light refracting and less light absorbing around the poles and the mid latitudes here. So Earth's heat budget. When we think about the heat budget, it's always going to try to balance solar incoming energy versus radiation going out. And that helps to determine global temperature stability. The oceans are invaluable in absorbing and redistributing heat around the globe. If it weren't for ocean circulation, we really wouldn't have an Earth that we could live on. And the atmosphere helps to act as a transport system for a lot of that heat. Here you see the Earth's heat budget. This is from your textbook, but you've got the incoming solar radiation, where about 30% of it is reflected right there at the beginning. And you see some of what's happening after the heat is absorbed and then radiates back out into the atmosphere. So convection cells in the atmosphere. Warm air rises at the equator, which I think makes sense to everybody. The air cools and begins to sink at around 30 degrees latitude. We'll look at a picture of this in a second. And that's what starts to set up a convection loop. And that's the basis for all these convection cells or circulation cells that we're going to talk about today. So again, we'll look at a map of this in just a second, but the Hadley cells are between the equator at 0 degrees and 30 degrees latitude. The Ferrel cells are between 30 and 60 degrees latitude. And then our polar cells are from 60 degrees up to the poles. And these cells drive global wind belts and our climate zones. So here you can see a map that shows our polar cells from essentially the poles to 60 degrees, the Ferrel cells from 60 to 30, and the Hadley cells from 30 to the equator. And the same thing in the southern hemisphere. So these work both northern and southern hemispheres. The Intertropical Convergence Zone, also known as the ITCZ, is an area of low pressure that's rising at the equator. Causes intense clouds and rainfall. It's essentially what makes monsoon season in a lot of tropical areas. And it moves around a little bit, which is why some areas have monsoon season at different times of their year. Subtropical highs. Air begins to sink again around 30 degrees in both the northern and southern hemispheres. That creates dry, stable conditions, and that's really where most of our deserts are found. So that's an interesting thing. They don't get as much rain there, and most deserts are found around that general latitude. And then the air flows back toward the equator or the poles from there. Then we have our polar front, starts at 60 degrees latitude. Warm mid-latitude air meets that cold polar air. That warm air rises and that creates storms. This is the boundary between the Ferrel and the polar cells, and it's an area where a lot of times there are more storms than other areas. People who live in this area will often get a lot of snow in the wintertime, thunderstorms, things like that. Global climate zones in general. These are belts of rising and sinking air that shape our ecosystems. So our tropics are wet, our subtropics are fairly dry, the mid-latitudes tend to be more stormy, and the polar latitudes are cold and dry. And this is all because of those belts of air that move around our globe. Again, this is a slightly different picture, but we have our polar cells up near the pole to 60 degrees north latitude. And then this is called the mid-latitude cell, but this is the Ferrel cell. You'll need to know the term Ferrel, from 60 to 30 degrees latitude. Our Hadley cell from 30 to the equator. This also shows the intertropical convergence zone. And we're going to talk more about the trade winds and the westerlies and the polar winds in a little bit in our next lecture. So basics for this lecture, we talked about the uneven heating that drives atmospheric movement. We talked about the 3-cell model. We've got our polar cells, our Ferrel cells, and our Hadley cells. Pressure belts shape climates around the world, and that is the foundation for the wind belts and hurricane behavior and really climate around the entire globe. So next, we will talk just a little bit more about those global wind belts, and we'll talk about the Coriolis effect.